Hey guys, wanted to take our moment here today to go over your motion graphs and your acceleration notes. So when we graph distance versus time graphs, which is what we'll see most of the time, and it's what you just saw in your buggy lab, um, on your distance versus time graphs, distance or position will be plotted on the y-axis, and time will be on the x-axis down at the bottom there. The slope of the line on a position or a distance versus time graph is always going to be the velocity of the object. So a positive slope tells us that the object has a positive velocity. A negative slope tells us the object has a negative velocity. And positive and negative just tell us direction here. So it tells us which way it's moving, either away or toward the origin. Um, a straight line indicates that it has a constant speed. So that line can still be sloped or angled. That's just going to indicate a constant speed, assuming it doesn't have a bend or any like turns in it at all. And then no slope, meaning a flat line, means no motion at all. Now we're going to look at some examples of this here. So we've got four different graphs here. Now this first one here shows that the position is not changing as time goes on, which means the object isn't moving. So this object has no velocity. It also has no slope on that line. Again, remember the slope of the line tells us the velocity of the object. So the slope is zero, the velocity is zero, and this object is at rest. Now the second graph here, we have a nice straight line, which as we discussed, means a constant speed or a constant velocity. It is also moving away, so we can see that this thing is moving away at a constant velocity. Here we have a downward slope or a negative slope. This tells us that the object is moving back toward us here. All right, it's got that, again, a constant velocity because that line is also straight. Now, this curved line shows us that the slope is changing. So the slope is not very steep here and it's very steep here. That means that the velocity is not constant and this object is accelerating. Now, velocity versus time graphs are a little less common, but we'll still see them from time to time. Velocity versus time graphs have velocity plotted on the y-axis, and again, x is plotted on time is plotted on the x-axis. The slope of the line is the acceleration of the object. So we'll be able to look at the acceleration of the object based on these graphs. So a positive slope gives us a positive acceleration. A negative slope gives us a negative acceleration. A straight line means a constant acceleration. And again, just like with the distance versus time graphs, that's still a sloped line of some kind. And then a line with no slope on a velocity versus time graph means no acceleration, or the object is traveling at a constant velocity. Here are some examples of this. So we can see we have a positive slope. This means that the object has a positive acceleration or is likely speeding up. No slope right here. This indicates that the object is going at a constant speed, or again, no acceleration because there is, again, no slope. And then a negative slope means that the object has a negative acceleration or is likely slowing down. Now, acceleration, just so we are aware of the definition here, acceleration is the rate at which velocity changes over time. So we're looking at how the velocity changes. Now, how can something accelerate? Well, there's three ways something can accelerate. The speed can change, so it can speed up, like a car accelerating from 0 to 60, or it can slow down, like a bus slowing down to pick somebody up at a bus stop. So speeding up and slowing down are two examples of how we can change our acceleration or accelerate, excuse me. Now, there's a third way that an object can accelerate, because acceleration is defined as a change in velocity, and velocity is a speed with a direction. We talked about how you can change the speed, but if you also change the direction, you can accelerate as well. So if you're riding on a Ferris wheel, you're traveling at a constant speed in that nice smooth circular path, but because your direction is constantly changing, you are constantly accelerating. Now, the equation we're going to use to calculate acceleration is this right here. acceleration is equal to our final velocity minus our initial velocity over time. All right. Now, what this does is it takes our change in velocity and divides that by how long it took us to change our velocity. So this looks at the rate at which we're changing our velocity, just like the definition said. Now we're going to go through a couple examples for this. The first example problem, a car accelerates from rest at 60 or from rest to a speed of 60 miles per hour in 2.1 seconds. What is the car's acceleration? So just like the other practice problems I went over with you guys, we're going to show all 4 steps for these problems. And again, the more work you show us, the better chance you have of earning the most possible partial credit, even if you get the final answer wrong. So please make sure you show us your work on any time or on any questions we ask you to do math. So the first step is identifying what the problem gives us. So we have 3 variables we need to identify here because we're looking for acceleration. So we need to find VI, VF, and T. So our VI is our initial velocity. Now, they only give us 2 numbers in this question, but they tell us that the car accelerates from rest, which means that the car is starting from a stopped position, which means our object isn't moving, and our initial velocity, or starting velocity, is 0 miles per hour. Now, our final velocity is 60 miles per hour. That's what we're accelerating up to. So 60 miles per hour is our final velocity. And then t, the time in which this occurs, is 2.1 seconds. So the second step is to identify our equation. A is equal to VF minus VI over t. And then we plug our values into this equation. So 60 minus 0. Now, guys, I will say it is important for you to make sure that you get VI and VF into the correct spots. Otherwise, it's going to change whether or not your calculation gives you a positive or a negative acceleration. So our final velocity always goes first. We subtract our starting velocity, which in this case is 0, and then we divide by 2.1 seconds. Well, I simplified the top here. So we have 60 miles per hour divided by 2.1 seconds. And that's going to give us a final answer of 28.57 miles per hour per second. Now, the units on acceleration are going to be a little goofy. Anytime you have mixed units like this, you're going to need to write out each one of them. All right, I'm going to show you an example of a slightly different scenario here on the next question. But you'll see here we have our velocity units per unit of time because we're looking at the rate at which the velocity is changing. So velocity per second, all right, or miles per hour per second. Now on the next question, we have a bus that was traveling 2.1 meters per second, and over the next 5 seconds, it slows down to a stop. What is the acceleration of the bus? So again, the first step is to identify what the question is giving us. Our initial velocity is 12.5 meters per second. VF is 0 meters per second because we know we're coming to a stop, which means we're no longer moving. And then our time is 5 seconds. I'm going to rewrite the equation that we're going to use, and then I'm going to plug our values into this equation. Now, again, it's really important that we make sure we have VF and VI in the correct spots. VF always comes first, so 0 minus 12.5, then divided by 5. So when we do this, I'm going to go ahead and simplify the top. That gives us a negative 12.5 meters per second on top, and then we're going to divide by 5 seconds. Now, when you plug that into your calculator, it's going to give you a final answer of negative 2.5 meters per second, or when the 2 time units are the exact same units, you're able to do this right here, negative 2.5 meters per second squared. If you ever see this, know that this is an acceleration unit as well, all right? Meters per second squared and meters per second are the exact same units. All right, ladies and gentlemen, that concludes our notes. I hope you guys all have a great day.